University. Professor Blair is an astrophysicist and research professor at Johns Hopkins and the current project scientist for the famous James Webb Telescope. Today, he will present information about the James Webb Telescope. And at the very end, we will have a short Q&A session if you guys have any questions. So without further ado, we'll hand it off to him here.
Hello, everybody. Let's just do a sound check. Everybody can hear me okay? I'll nod ahead or something so that I know my sound. Yeah, okay, that's good. And you can see the slides all right. Very good. So very pleased to be with you today to tell you a little bit about the Webb Space Telescope. Of course, it's been up there a little over a year now, but it's been in science operations for just over 6 months now. So it's still a pretty new telescope. It's everything gone very smoothly in terms of getting it up there and getting it checked out and calibrated for science. And so it's up there working 24/7 right now, doing a lot of good stuff. I have just very recently retired from the project after working on the Webb telescope for 13 years in terms of preparing the systems that will support the telescope while it's up there and supporting the astronomical community in using and proposing for and using the telescope. So let's see here. Will it let me go forward? There we go. Okay, so first of all, I just wanted to mention that the Webb telescope, it's been many years in preparation, of course, for launch. And here we have a few pictures of it on its way to the launch pad. On the left side is a picture at Goddard Space Flight Center where the telescope mirrors and the science instruments were put together into one part of the package. The next picture is down at Johnson Space Center where it spent several months inside a large vacuum tank simulating the conditions of space to make sure that it was all working properly. And then that part was shipped out to Northrop Grumman, the next picture, down in Southern California, where the telescope and the science instrument were put together with the spacecraft part of the observatory. That included the sun shield, which you see there folded up right now in this picture. And here's the telescope and the instruments back here that were going to be put together with that. That all went through a lot of testing for a long time at Northrop Grumman. And then here's the photograph of December 25th, 2021, just a little over a year ago, when it launched on an Ariane 5 rocket. Now, the Ariane 5 is a big, the heavy lift vehicle for the European launch facility. And that was actually part of their commitment to the project, was to supply the launch vehicle, which did a great job for us. So it really is an international project. Canada provided us with the guide camera and one of the science instruments. The European Space Agency provided the launch, like I mentioned, but also major parts of 2 of the science instruments, as well as a lot of technical support. And of course, NASA is the prime part of our involvement. But the European Space Agency represents 17 different countries. So it really is a very wide international project. So there's a picture of me just outside the control center, which is in Baltimore. I don't know where all of you are. I didn't have time to ask, I guess, but I'm in Baltimore and work at Johns Hopkins University, and the Space Telescope Science Institute is on the Hopkins campus, and that's where the Webb telescope is operated from. And there's a graphic here on the right that shows kind of what the telescope would look like on orbit there. The sun shield is all protecting the payload itself from sunlight. And of course, the telescope would not be visible like it is in this graphic. It would be completely dark on that side because it has to stay on the dark side of that sunshade in order to get cold. And the Webb is an infrared light sensitive telescope. And so that's why it needs to get cold. Infrared, of course, is just heat, radiation. And so if it's going to sense very faint heat signals from across the universe, the telescope itself has to be very cold, or it would just be overwhelmed by the heat of the telescope itself. So, okay, here's a couple pictures of the control center itself there on the Hopkins campus. It's a little different than Hubble. Now, the institute there, the Space Telescope Science Institute, operates the science operations for the Hubble telescope, which is planning the timelines and interacting with the observers to get their proposals into the system and so forth, scheduling the timelines. But NASA actually talks to Hubble. The Webb telescope is actually both the science operations and what's called the mission operations are done right there in Baltimore at the Space Telescope Science Institute. And here's a couple shots of that control center where that all happens. For the first 2 weeks after launch, if you followed this back when it happened in early 2002, the first 2 weeks were spent basically getting the telescope from its launch configuration into its final configuration. And that involved, of course, the sun shield deployment steps and getting those 5 layers all separated and working properly. And then getting the telescope itself all set, which meant putting the secondary mirror in position and then unfolding those 2 wings of the mirror that were folded up for launch to make the primary mirror. And finally, then the fully extended telescope at the lower left here in this picture. Now, it still took it another couple of weeks after that, cruising on its way out to what's called the Lagrange 2 point, a spot about 1 million miles out away from the Earth. But is a kind of a special place in space because the gravity and centrifugal forces of the orbit balance out to keep that telescope right with the Earth as we go around the sun. So normally something that would be farther away from the sun would orbit slower and would drop away from the Earth orbit. But this special spot allows the Webb telescope to actually kind of follow with the Earth as we go around the sun. And we keep that sun shield toward the sun, keeps the telescope on the dark side, and allows it to get nice and cold and sense the infrared light. So that whole checkout period after it got out to the Lagrange 2 point, which took about a month, it took about another 5 months after that to get it all aligned and focused and all the calibration done for the instruments and get it ready for actual science operations. So that was just in mid-July when that all happened. This is just, I'm not going to go through all this. This is just kind of an eye chart, but basically a lot of things had to happen before it was ready to do science. And this is just a graphic that kind of shows some of that. The green part here on the right is the getting the telescope and the mirrors all aligned and ready to go. And then the second half of that period was all getting the science instruments calibrated and getting them ready to go. And now we've gone into science operations. Okay. Well, this is back on July 12th in front of the Space Telescope Science Institute. And here's just some of the people that worked on the what's called the commissioning period, the 6-month period of checkout for the telescope. And that was right about when they first let out the first pictures from the telescope in July last year. So here's me and my wife up here in the upper left. We're actually down here too in the picture, but there are many people. Of course, there are over 600 people that worked on commissioning. This is only part of the ones that were at the Space Telescope Institute. And actually, they estimate that it was close to 20,000 different people, contractors, different university groups and whatnot. 20,000 people worked on the Webb telescope at some phase or another during its construction and testing phase. So that was exciting. I mostly put this slide up to make sure that you know that you can go to webtelescope.org, which is your one-stop shopping for all kinds of public outreach content from the mission. And they do a great job, not only with putting the pictures out there, but explanatory content and other information that you might find interesting. So WEBB telescope.org is your one-stop shop for lots of information, including some of the stuff that I'll show you today. So this is kind of an odd place to start, but I wanted to make the point that oftentimes when we see pictures, whether it's a wide angle picture like this of the sky or a Hubble picture or a Webb picture, that there is tremendous depth into the screen that is not real obvious. Here we are just projecting this picture onto a nice flat, computer screen, but here we see a picture that's got the Earth in the foreground, so that's very close to us. We've got a comet, which is part of our solar system. We've got all these stars on this big band going across the sky, which of course is the Milky Way, which is the edge-on part of our galaxy. Of course, all these stars in the picture are part of our Milky Way galaxy. And then you see these two smudges off to the side here, which this is a picture taken in the southern hemisphere. And those are nearby galaxies called the Magellanic Clouds, the Large Magellanic Cloud and the Small Magellanic Cloud. That's about 160,000 light years away. And the Small Magellanic Cloud is about 200,000 light years away. Of course, that's the distance. Light years, the distance light travels in 1 year. You all probably know that. But 200,000 years ago is when the light left that galaxy that we're capturing in this picture. So there's tremendous depth in this picture that's not maybe obvious from looking at it. And that's definitely true for some of the things that I'll show you for the distant universe taken with Hubble and now with the Webb telescope. But it's also a reminder that this is the way astronomy was done for thousands of years. This naked eye universe is all we had to work with until 1609, when Galileo first turned a telescope to the sky. This doesn't want to go forward. There we go. So I just wanted to highlight the fact that astronomy is probably different than just about every other science that you can think of, because it's hard for us to go out and sample a galaxy or a quasar and bring it into the lab and look at it. We can't do that. They're too far away. All we have to work with is light. And when I say light, I mean there's lots of different kinds of light, and astronomers like to use all different kinds of light. And as an example, radio waves is just a different kind of light. Infrared, optical, ultraviolet, X-ray, even gamma rays are all different parts of what's called the electromagnetic spectrum. And while the Hubble telescope works mostly in the optical and a little bit into the ultraviolet and out the red end of the optical spectrum, but really not very far into the infrared part of the spectrum, the Webb telescope really just works here in the infrared light part of the spectrum. And infrared light is just heat. It's just a different kind of electromagnetic radiation. And so here's a little graphic that kind of shows the electromagnetic spectrum from short wavelengths or high frequencies in gamma rays and X-rays at this end through the optical part of the spectrum, into the infrared and into the radio part of the spectrum here. And this line is intended to show you what gets blocked by the atmosphere. 100% opacity means that the atmosphere doesn't let any light through. And then there's a window where the optical light gets through. And there's a messy section of infrared where the Webb telescope works. It's very hard to do from the ground. And then there's a big open radio window. It's probably not surprising that after optical astronomy, radio astronomy was the next band that really started to observe the universe, because that gets down to the Earth's surface. But a lot of this other stuff gets blocked by the atmosphere. And so we have to get satellites up there to observe in these other kinds of light. And astronomers want to use all these different kinds of light because things look different in different kinds of light. And I'll talk about that a little bit. Here you see the area where the Hubble telescope works, and then where the Webb telescope extends out to longer wavelengths and into the infrared part of the spectrum, where we really don't get through the atmosphere very well. So you say, well, we've got the Hubble telescope up there. Why do we need Webb? Why do we need these other telescopes? Why do we need big ground-based telescopes? Well, each telescope and the instrumentation on that telescope is like a new tool for astronomy. If you kind of make the comparison to a carpenter, they have different saws for different jobs, different tools for different jobs. Even though they're all saws, even though these are all telescopes, they're all the same sort of tool, but they do different jobs for astronomers. The same thing with, you could say screwdrivers if you want to, instead of, or hammers, different kinds of hammers, different tools for different jobs. And that's really what the different telescopes and the different kinds of light and the different kinds of instrumentation then that are specialized to those light detection methods are used in astronomy. And so it's not like one thing supplants another one completely. And not to forget about the Hubble telescope, which is still up there operating since 1990. It's been up there now for almost 32 years in April. It's amazing how well it is still operating, because it hasn't been serviced since back in 2009. And the graphic on the right here just gives you an idea how big that telescope is compared to something you're a little more familiar with, a bus. There, next time maybe you see a bus driving down the street, you'll think there goes the Hubble telescope, because that's about the size that the Hubble telescope is. And then just for comparison, I'll get to that in just a moment. I want to just say that those different kinds of light that we observe show us different things about the same object. And this is just one example I'm going to talk through. This is a picture of Messier 82, the Messier catalog of galaxies. It's spelled Messier, and it is one of the Messier galaxies. As you look at it, it's pretty a lot of stuff going on here. The green light you see is a Hubble picture that's showing the starlight. It's basically kind of an edge-on view of a spiral galaxy. And then in the red light, we see infrared light from the Spitzer Space Telescope, which was a smaller space telescope that looked at infrared light. And I'll talk about that a little bit more in a minute. And also the Chandra X-ray Observatory, which looks at X-rays, and that's the blue light you see in this picture. And so those kinds of light, infrared and X-ray, of course, are not visible to our eyes. So what happens here is that astronomers assign a color to the X-ray, a color to the visible light, a color to the infrared light, and they put them all together in one picture, and you see what looks like a color picture. So what are these different kinds of light telling us about this galaxy? Well, it turns out that there's a tremendous burst of star formation going on down in the center of this galaxy. And you see that in the visible light, but a lot of that is blocked by dust in the visible light. So you see the extended galaxy, but you don't really see the starburst. And in dust, we see all this material that looks like it's not in the plane of the galaxy, but blown out into these bubbles above and below the plane of the galaxy. And inside those big shells of dust is this hot X-ray gas. And what's happening here is that the winds and the supernova explosions down in the center of this galaxy are blowing out these big bubbles of hot gas. And on the edges of those bubbles is where the dust forms around, and that will eventually start a new generation of star formation from that dust and gas that's in the shells that are swept up by these big hot bubbles coming out from the starburst. So again, just an example, different kinds of light are telling us different things. If you just looked in Hubble, you would just see this band of light going across the middle, and you wouldn't see all the rest of this action out here. Okay, well, let's talk a little bit about the Webb telescope now. Here's just a couple of graphics, again, showing the telescope on orbit. On the left here, you see what we would call the hot side of the telescope. This is the side that would be facing the sun. And this is where it's got the rockets that are used for station keeping and actually for getting it out to its orbit out there. The solar panels, the electronics for all the instruments and so forth are on the hot side, if you will, of the telescope. And then on the back side of that big sunshade that's been unfurled is the telescope and the science instruments themselves. And this version on the right, you can see the telescope a little bit better, and the science instruments are back here behind the main mirror. So in that picture, the light from a distant object would be coming in, hitting the main mirror, coming up, hitting the secondary mirror, going down through this opening in the mirror to the back side here. And this is where the science instruments are that sense the infrared light and turn it into ones and zeros that gets sent down by the electronics down to the Earth. And the radio antenna that does that is on the hot side of the telescope. So that's how it was designed. That's how it works. And here's a little graphic to give you an idea of the relative sizes of the Hubble telescope, which you saw. That's the size of a bus right there. And here's the Webb telescope. And over here is a little graphic I put in of the Spitzer Space Telescope. In many ways, the Webb is a follow-on to the Spitzer telescope, more so than it is a follow-on to the Hubble telescope, because it looks largely in the same part of the infrared part of the spectrum. And here's the size of the mirrors. And you can see that basically the Webb mirror is about 58 times larger than the Spitzer telescope, which allows it to do a lot more, see a lot more clearly, as well as collect the light, much more light from distant objects and so forth than the Spitzer telescope. And it even collects 7 times more light than the Hubble telescope does, because of the size of this big segmented primary mirror. You can see there's 18 separate mirrors that work all together to like one big mirror to make the Webb telescope work. Plus, of course, there's a mirror up at the secondary, and there's mirrors in the instrument package as well. So the Hubble telescope here again looks at ultraviolet, optical, and just a little bit into the infrared. And then the Webb telescope picks up there and looks farther into the infrared and actually overlaps with where the Spitzer Space Telescope worked. And it's not shown here, but this is actually a log scale. So this area of overlap is a lot more significant than it looks like in this particular graphic that I found here. Okay, so it's a big telescope, biggest telescope we put up there. Here is just a comparison of a Spitzer image of one area of the sky and the same area of the sky observed with the Webb telescope. And I don't know about you, but if I was working on these data, I'd rather work on the data on the right side of this picture. It's just fabulous. And I mean, just look at all the stuff in the background. Those are all galaxies out in the distant universe. You see some bigger galaxies that are relatively nearby here, a couple of stars. These things with the points on them like this are always either stars or things that are so small in angular size that they look like stars. And you see the diffraction pattern from the edges of the mirrors. And that's what gives it that six pattern, is what you'll see with Webb pictures. Okay, but there's a pretty good comparison. This is really what Webb has done for us compared to what Spitzer was able to do over here. Okay. I want to just talk a little bit about the telescope itself, because it's just such an engineering marvel. The mirrors, here's one segment of the mirror with some peoples that give you an idea of the scale. There are 18 segments like this into the main mirror, and they are coated with gold. Gold is the most reflective surface that we can put on the mirrors that reflects infrared light. And so that's why they used a gold surface on the mirror. If you took all the gold on all the mirrors of Webb and put it in one place, it would be about the size of a golf ball. So they're very, very thin layers of gold that are spread over that whole mirror, but it's not very much total gold that was deposited on those mirrors. The mirrors are made out of an element called beryllium. Beryllium is really strong for its weight, and it doesn't change a lot when you change the temperature. It's called thermal coefficient of expansion, is very low. And since they had to manufacture the mirror in a lab at room temperature, but it was going to work at 40 degrees above absolute zero, you had to have something that would hold its shape well as it went down to cold temperatures. And so beryllium is what they're actually made out of. Now, beryllium, as it turns out, is very dangerous and difficult to work with in the lab, and they had to do all kinds of technology development to figure out how to use that material to make the mirrors. Then there's this big sunshade. You can just imagine the complexity of having the 5 layers of sunshade that had to all be squeezed together and folded up for the launch, and then had to unfurl properly once they got up there. That was another bit of technology development as well. And the reason there are 5 layers is both to protect against small punctures that might go through one layer, but are certainly not going to go through all 5 layers of that sun shield. But more importantly, from a thermal standpoint, the sunlight hits, in the picture on the left, the sun would be coming from the bottom and hitting the bottom layer, but now it's turned on the side over here on the right. The sunlight comes in and hits that first layer. Most of it gets reflected. What does get through that first layer mostly then is blocked and escapes out the sides, but some gets through to the next layer. And then some of that escapes, some gets to the next layer and the next layer. It turns out that there's over 200,000 watts of solar energy hitting the sun side of the sun shield, and only 1 watt of energy gets through to the backside where the telescope is. So just by keeping the telescope in the dark on the backside of those 5 layers, keeps it cold and allows it to see this infrared radiation, which is, like I said, heat radiation from objects well across the universe. And the science instruments, I won't go into detail here, but there are 4 primary science instruments. There are 2 prime cameras, a near infrared camera and a mid infrared camera. And they also have spectroscopic capabilities of certain kinds, but there's a specialized near infrared spectrograph on this side, and another near infrared instrument here that also has the guide camera built into it. And that whole structure is what sits here on the backside of the telescope structure. So that whole massive thing is what sits on the backside of the telescope mirror and senses the light. And I thought I'd just show one picture here, because this unassuming looking device here is one of the devices that actually senses that infrared light and turns it into electronic signals that we can then reconstruct after it's radioed down to the earth and calibrated. We can reconstruct that into a picture. And these devices are very complex things that have been actually designed specifically for for the Webb telescope. Here's a package of 4 of them in one of the cameras that goes together. And then as you take a picture, you move the field of view around a little bit, and you can remove the impact of these divisions between the different parts, and you just take one picture of the whole area there, but you take multiple pictures and stitch it together. That's called dithering. It's a very important thing that they do to make the images that you'll see. Okay, and I mentioned that it's a new tool for astronomy. It's actually a Swiss Army knife. There's a lot of different science instruments on this package, and what you'll mainly see are these 2, which is the near and mid-infrared imaging. But there's spectrographs that break the light up into spectra. There are coronagraphs on board that actually block out the light of a bright object and allow you to look for planets or a disk of. I didn't want to do that. Here we are. Sorry about that. Coronography is what blocks out the light from a bright star, eclipses a bright star essentially, and allows you to look in around it to see a disk of planets forming around other stars and that sort of thing. And I've actually showed in green that there are near infrared instruments, and then there's this mid-infrared instrument that are the capabilities are shown in red there. And the reason I broke them out like that is to just make the point that the optical light spectrum, it goes just about over a factor of 2 of wavelength, from about 0.35 to 0.7 microns, or from 3,500 angstroms, if you will, to 7,000 angstroms or so. The infrared spectrum here that the Webb telescope looks at, just the near infrared part of it, goes over a factor of 5 in wavelength, from 1 to 5 microns. And then the mid-infrared instrument goes from 5 to 25 microns, another factor of 5. So the Webb telescope is looking at a factor of 25 coverage and wavelength, whereas the optical light, like the Hubble telescope, looks over just a factor of 2. So they have specialized instruments for 2 different parts of that whole spectrum of light, and they had to develop new technology for each of those parts of it. So, okay, so I want to get into this science a little bit now, and I hope if you have questions, I hope you're holding on to those, and we'll get to those at the end. I could take a break here and take questions, but maybe I'll just chug along through this. Is that all right? And we'll take questions at the end. So a telescope with that kind of capability is going to do a tremendous breadth of science. There were 4 main areas of science that were highlighted in getting the telescope approved by Congress and so forth. It took a lot of money to build this telescope, and what do you think you're going to learn? Well, you had to have some key science programs, and so there were 4 general areas that were highlighted before it launched, but it will do many other things in addition. But let's just kind of use them as a framework for talking about this. The early universe stuff, if you have heard of the cosmological redshift, what happens is as we look at objects that are farther and farther away, their light shifts from the ultraviolet to the optical to the infrared and farther into the infrared as you look farther and farther away. And so even though Hubble had been able to look pretty far, if you wanted to look farther than Hubble could look, it couldn't do it. The light had shifted right out of Hubble's range and into the infrared. And so to look at the earliest galaxies and stars that formed in the universe, we needed to have a telescope that looked farther into the infrared part of the spectrum. And that was one of the main things that Webb was supposed to do and has already started doing. Of course, you see all the galaxies between you and that early universe, that whole depth thing that I was talking about on the early slide where you look way out into the universe and all these little flecks in the background are the distant things. And you see everything else along the way too. So you can study the evolution of galaxies over time as well, and how they interact with each other and form larger and larger galaxies. In our own galaxy, we can look at stars that are forming. We can look at stars that are dying, the stellar life cycle. And in particular, oftentimes there's a lot of dust and gas in the way of those processes when stars are forming, and we have a hard time seeing into where that's going on and understanding what the physical mechanisms are in there. Well, when you go to the infrared, it turns out you can start to see through some of that dust and actually get in and study some of the things that you couldn't see at visible wavelengths. And then also, remarkably, we can look at planets around other stars, whether or not we can actually see the planets themselves and study sometimes by their absorption of light from their host star, we can study the atmospheres of stars, of planets around other stars, other worlds, exoplanets, that's called. So let's take a look. It's not too surprising that the first results that were released actually had something in each of those 4 science areas. And let me just talk through those briefly with you. So here I just wanted to make the point again that some of these pictures you're going to be seeing, which have, beautiful color pictures, what you're looking at is infrared light that your eye can't see. And what happens is you take, let me just look at the one in the upper left here. These are the band passes of the various filters on the MIRI instrument. And so if you took a picture with this one that's called F770, and maybe one with this F1500 and one with F2100, and made this one blue and this one green and that one red, you're going to get a color picture out of that. But what you're doing is showing different infrared wavelengths. And the reason that's interesting is in this bottom thing here, what I've done is I've projected the spectrum of a particular object underneath it. And you see it's got some bright places and some bumps in the spectrum and whatnot. And by picking different filters, you can isolate different parts of the spectrum of an object. And so the light that you gather in these different filters tells you different things, again, about the objects that you're observing. Okay, so when you see these color pictures, just remember that you're looking at infrared light, and they're pairing up these different filters in ways that produce a good picture, but also then they have some physical meaning to them, some content, some science content to them as well. Again, just kind of for scale here a little bit, this is the Carina Nebula, which is a big star-forming region in our own Milky Way galaxy. This is a ground-based picture of the larger Carina Nebula. And off to the side here in this little white box is a separate little nebula that's part of that whole complex that's blown up over here on the right. And I put a white box here that shows a blow up at lower left here. And remember, the stars are out to the left side here that are eating into that big dust shell. And now here's the Webb picture. You have to turn it 90 degrees or 100 degrees to get that orientation. And that's the region that we're looking at, a tiny, tiny piece of the sky in very great detail. And that's the job of the Webb telescope. It's also the job of the Hubble telescope. Here's the Hubble picture of the same region, and here's the Webb picture of that same region. And even though, again, the colors look kind of similar, that was done by the people putting the pictures together. These are optical wavelengths, and this is infrared light wavelengths. And again, you see, look at the detail that you see in the Webb picture. And also you get a sense that you're kind of seeing through some of the dust here a little bit. You see there's more stars in here that you can't see coming through the Hubble picture and whatnot. But you see comparable quality data from those two telescopes, complementary data from optical and infrared. Now here's the NIRCam picture again up here, and I put a box on that one, and the field of view of the mid-infrared camera is a little bit smaller, and so this is the area that it observed, just a piece of that NIRCam picture that I'm showing down here below, and so that's the even longer infrared wavelengths that does even a better job seeing through. You see all these background stars showing right through the dust here, and I've put a box on this little object here off to the side. And you can see in the even in the near infrared to Webb, that it is shrouded in gas, but it's very bright there. But you're actually seeing the star that's buried in there as you go to the mid infrared. And again, it's those longer wavelengths look through the dust better and allow you to see what's going on inside in the star forming region. Okay, I could talk a whole colloquium about that particular picture, but let's look at some other ones. So now here's another Hubble versus Webb comparison of the Southern Ring Nebula. This is an object called a planetary nebula. This is a star that's at the end of its lifetime, and it is shedding its outer layers. And so that nebula you see around and the cavity around it is being blown by the wind from the core of the star in the center that's losing the material. And it's blowing a wind out that's sweeping up a shell of material around it. And here's what it looks like with Hubble. Here's what it looks like with the Webb telescope, and in particular, they've chosen for the red one here, the red band, a wavelength that is showing you molecular hydrogen, which is very cold molecular gas. That has the most structure that you're going to see, and you can see all the detail in that outer structure from the molecular hydrogen in that gas. And again, if I compare this near infrared picture to the far infrared picture, there's another surprise that came out. And up here in the upper right of each of these, I've just blown up the very central portion of these two pictures. But it turns out that the star that is losing the material of this nebula is not the one that you see, not the one that Hubble saw, and not the one that we see here in the near infrared. But when we come to the far infrared, there's a second star there. That's the one that's actually losing the material. And this other star was a binary companion. They were actually in a orbit around each other. And it's the star that's being left behind, the normal star that we see in the near infrared and in Hubble, and in the far infrared, we finally see the star that's actually losing the material. So that was pretty cool, I thought. And again, you see the different filters that went into that, or the different wavelengths of the far infrared light that we were showing in that picture. That's why the colors changed from one to the other. They just chose different bands. Okay, this is moving out a little bit now. So we're looking at a grouping of galaxies that's been known for a long time, called Stephan's quintet. Quintet means 5, and you only see 4, but there's actually 2 here that are merging together in the middle of this galaxy. And here's the Hubble picture. And you can see this one galaxy, it kind of looks different than the other galaxies to Hubble. And that's because this is a chance superposition of this galaxy with these galaxies. This one's only about 40 million light years away, and these guys are almost 300 million light years away. So these are in the background, and this is in the foreground. It's just a chance position that they happen to be close together on the line of sight. But here's now the infrared, the near infrared picture over here on the side, and you can see all the galaxies look white. Here, Hubble is being affected by the dust in these galaxies, and the dust scatters the blue light away, and you see them looking kind of reddish in color. And for Webb, it looks right through that dust, and so you see into the stars, and they all look kind of whitish in color because you're seeing the stars mostly in the near infrared. And then here in the background, this is just a little piece of this background that's blown up, so you can see all the galaxies in the background. That's seen in almost every Webb picture. You see the background is just littered with galaxies that are off in the distant universe behind the objects. Here's a comparison now of the near infrared again on the right-hand side here that you saw before, and I put a box around the region that's shown now in the mid-infrared data, and you can see they look quite different. Not only the colors are different, but the structures that you see are quite different from what you see with Hubble. And I had an arrow pointing to this thing. You see this object with the diffraction spikes on it. That means there's a very small star-like object in there. Well, it turns out there is a black hole in the center of that galaxy that is very bright when you can see into it. It's accreting material, and it gets very bright and close to it. But there's so much dust in the way that even at near infrared wavelengths, you don't see into where that black hole is. And yet when you go to the mid infrared, you see these diffraction spikes, and it means you're seeing a point-like source in there, and that's the accreting black hole in the center of that galaxy. So that's kind of cool. It does highlight that this nearby galaxy looks quite different in these colors that they're showing here, looks quite different than the ones that are more distant, more farther away. And you see a lot of material that shows up in the infrared that just barely is even visible to Hubble or to ground-based telescopes. And that all tells you part about different physics of the interactions that are going on. And again, I'm showing you mostly images here, but that's a lot of physical information in those images. Here's actually the first picture on the right here is the very first picture that they released from Webb, and it's called a deep field picture. It's actually showing a galaxy cluster, and so these whitish galaxies you see are the galaxy cluster that's relatively nearby at 4.6 billion light years away, and all those other galaxies you see are farther away than that in the background. And you see there's just a few stars in the picture as well. I'll come back to this in a moment, but here's actually a galaxy up here that has another black hole in it, and you see this diffraction pattern from that one that gets very point-like, and you see it. On the left here is the Hubble picture, which is not quite representative because Hubble could do a better job on this, but this was the Hubble data that we had available for this cluster before Webb took the picture on the right. And so in that sense, it's a fair comparison, but Hubble could do a deeper job than this picture shows. But nonetheless, this is a tremendous step forward in terms of the detail that we can see. And of course, we're looking at a different kind of light. And let me just highlight the fact that these pictures that you're seeing are from really very tiny pieces of the sky. This is actually a picture that's showing the Hubble field of view, but the Hubble field of view, camera field of view, is really not that different than the Webb field of view. And so I don't have a separate one for Webb, but it's very similar to this. Here for scale is the full moon. That's about 30 arc minutes across. And the field of view that we're looking at here is just a 2 or 3 arc minutes across, a very small portion of the moon in size. And yet this is the detail that the Webb telescope is seeing in that small little piece of the sky. Incredible, just incredible. The other thing that we're seeing in that picture, and I'll show you that picture again in just a moment, but I wanted to show you this example. You're seeing an effect called gravitational lensing. Now, you know, E equals mc squared says energy and mass are equivalent. They're just different forms of the same thing. And light can actually be bent by gravity. Its direction of motion can be bent by gravity. And this graphic at the upper left shows that you have a big cluster of galaxies in this graphic. And here's a background galaxy, and Earth is way over on this side of the diagram, of course, not to scale at all. And as the light from that galaxy is trying to come off in this direction, the gravity of that massive cluster of galaxies bends it and distorts it, and it magnifies it, and it comes to Earth, and it's called gravitational lensing. The mass of this cluster of galaxies is actually lensing. It's not a perfect lens because it's distorting the light. And in this particular example, you see this flare of bluish white light. It's the same galaxy and its light being bent by the mass of this cluster of galaxies into our line of sight. And here's the orange one is another galaxy that's being distorted by the gravitational lensing. So these are background objects way in the background, and their light is magnified, but it's distorted as it comes through this imperfect lens of a big, massive galaxy cluster. But it allows us to see things that are much, much farther away, and it does magnify them up so that we can see them in more detail, even though it does distort the shape of the objects that we're seeing in the background. Okay, if it's lined up just perfectly, you get something that's called an Einstein ring. And here's an example from Hubble this is actually a JW image, but Hubble has seen the same thing, where the host galaxy that's doing the lensing is here in the middle, this blue object, and there's a background galaxy that's actually spread out almost into a perfect ring instead of these arcs that we're seeing over in the example at the right. So now let's go back and look at this picture from Webb again. And I've just taken those 2 boxes and blown them up on the side so you can see them in a little more detail. Because here, you can see these brighter ones pretty easily and how their lenses are arced and whatnot. But look here in the background, there's all these little ones that are also being lensed. Those are all background galaxies that are being distorted and lensed by the whitish galaxies that you see here that make up this galaxy cluster that itself is almost 5 billion light years away. And you're seeing galaxies here now that are lensed from way behind that out to 10 whatever billion years behind the cluster. It's just absolutely amazing data. It's amazing the universe provides us with this incredible laboratory to look at these very distant galaxies, even though we have to figure out what the distortion from the galaxy cluster is doing. I told you again that we have pencil beams looking way out into the distant universe, and these brighter galaxies that you see in this picture, of course, are 5, 6, 7 billion light years away. But all these little flecks that you see here are actually galaxies in the background. They're actually distant galaxies. And in this particular graphic now, we've picked out a few of these guys that we've actually taken infrared spectra of, and those spectra are shown here on the right. And what you're seeing here is a pattern of lines, the hydrogen line, these 2 oxygen lines, and another hydrogen line that are normally in the visible part of the spectrum for a local galaxy. But even for this first object here, that is the first spectrum, is shifted into the infrared part of the spectrum. Here we are in the Webb wavelength range from 1 to 2, 3 microns here. Okay. And as we look at even more and more distant galaxies, you see the light shifts farther and farther and farther into the infrared until these lines that are already shifted from the visible spectrum all the way into the infrared are now being shifted from the near infrared part out into the mid infrared almost. They're so far away. And these little flecks of galaxies that are in the background here that don't look like much are actually the distant universe things that Webb was designed to see for the first time. And they're going all, this particular example, going all the way out past 13 billion light years back toward the Big Bang. Of course, the Big Bang was about 13.8 billion years. And these are no longer the record holders. We've actually pushed this back even farther in some other fields with Webb, and that will probably continue to go on for a while as they look at more and more areas of the sky. So pretty incredible. Okay, now we're going to swing way back in toward our own galaxy and nearby stars and look at some exoplanets. And so there are a few cases where we can literally see the planets around other stars, but those are few and far between. Those are special cases, but there are many, many more cases, excuse me, where we can sense the presence of a planet around another star without actually seeing the planet directly. And we do it by this, what's called the transit technique, where as the planet, if we happen to just look at a whole bunch of stars, some of them we're going to get lucky and find that their planets and their solar system, if you will, is right in the plane that we are observing, so that as the planets orbit their sun, they get between us and the sun and block out some of the sun's light, that their host star's light. So all we are doing is staring at a star and staring at it and staring at it, and all of a sudden you see the light dips down for a period of time and then comes back up again. And that's because a planet, a host planet, has gone between us and the star and blocked out some of the light. And then it goes around the backside again, and you can see a dip there as well. So that's already incredible enough. You can tell an awful lot about a planet, its mass, its size relative to its star, and so forth, just by measuring these transit light curves. But now I want to take one more step and say, let's imagine that this planet actually had an atmosphere around it. And that's what this light gray is around the dark gray. It's supposed to just represent an atmosphere. Of course, it would be just a little thin layer around it, not as big as is shown here necessarily. But as the light from that star goes from the star to the telescope, to us, some of that gets absorbed by the atmosphere right around the edge of the planet. Okay. And if we get high enough signal to noise and look at enough different wavelengths, and this is actual Webb data over here of transit curves, and it's not obvious just looking at this, but some of these curves are a little deeper than other ones, and you can reconstruct the spectrum of the light that is being absorbed by the atmosphere of a planet that we cannot see around another star. It's incredible that they can do this. And that's basically what has been done here. And then, again, this is one of the first results that Webb did in this area, and it will do a lot better job as it increases the number of observations it takes on this particular planet and on other planets. It's already taken better data than this, but this was the first one that was resolved. And so this is called a spectrum, right? It's light as a function of wavelength here, but it's in the infrared part of the spectrum. And you see these bumps and wiggles. The blue line is a model that's been fit to the data. And that's the bumps that you're seeing there are models of what water vapor would look like in the atmosphere of that planet. And what it's showing us is that this planet that was observed around a little star called WASP 96 has water vapor in its atmosphere. And that's done through this process of transit spectroscopy, it's called. Pretty incredible. Here's a little higher signal to noise data now on that same planet, where they're looking just at one band. This is now carbon dioxide band at about 4.5 microns. And there's different models being fit to the data, but the points with the little error bars now are the actual data that they gathered over time. That's a little higher signal to noise. And you can see that it also has carbon dioxide in the atmosphere of that planet. Very difficult observation, very time consuming, difficult observations have to be timed just right to catch the planet as it's going in front of the star. And you have to do that multiple times to build up enough signal to noise to make this kind of a measurement. But here's one that they've already done, and they'll do more, of course, as time goes on. And we'll get statistics on a number of different kinds of planets. Okay. Well, there's a lot more that's been released since those early release pictures. And again, I just wanted to show you a few examples. Here's a nice example of a Messier 74, a relatively nearby face-on spiral galaxy. Here's the Hubble picture on the left, and here's the Webb picture on the right. And in the middle, they've put them together, scaled properly so that you actually see the Hubble data with the blue stars in the background, and the Webb data showing these holes that have been blown, some of them large and some of them small. Those holes are blown by star formation as the winds and supernovae move the interstellar gas around and dust into these shells. And by studying the statistics of the sizes of those shells and how many stars are doing that, we understand what the energy input is into the interstellar gas of that galaxy, and we can understand how that galaxy has evolved. And that's one of many galaxies now that have been observed this way. And I just wanted to show you again this tremendous advance. Here's now what the Spitzer telescope did on this same galaxy, and you can see the improvement from the middle to the right, from Spitzer to Webb, in terms of the spatial resolution that we get. We're looking at things in our solar system as well. Here's a picture of Jupiter that was taken early on during the commissioning period. But even from these commissioning data, you can see, and again, the colors are just chosen with different filters to show different things. What you're seeing here, the orange bands top and bottom are actually aurora, north and south auroral bands on Jupiter. Those have been seen in the ultraviolet light as well. And here we're seeing them now in the infrared as well. That's actually material that is being accreted from, with the ionized material that's being accreted from Io, one of its moons, onto the north and south poles along the magnetic fields lines of Jupiter, and it causes these aurora top and bottom. Here you see actually that they're picking up the faint dust rings that are also around Jupiter, and you see some of the moons actually getting picked up here as well. So they'll do lots and lots of stuff on solar system objects, although it's difficult observations for Webb because solar system objects are so bright, and Webb is such a big telescope. It's actually hard for Webb to look at these very bright objects. But here's another example of some star formation stuff that's going on with the infrared. Now on the left here is a Hubble picture of a star forming region in the small Magellanic Cloud, one of those little nearby galaxies that I showed you in that very early naked eye picture. This is a small region of that galaxy where stars are forming. You can see a cluster of stars that are formed in the center here. There's another cluster a little bit older up here that had formed earlier on. And the blue light that you see here is actually reflected starlight off of dust. The dust happens to be the dust grains are about the same size as the blue wavelength of light, and so it reflects the blue starlight, and you see this blue, what's called a reflection nebula here, but you don't really see the gas and stars that are forming very much. You see a little bit of dust here. This brown stuff is interstellar dust. Well, here's the same region now observed with Webb, and now you could hardly see the cluster of stars here that is in the middle because they're so blue and ultraviolet light that you don't get much light in the infrared. And so those stars almost disappear. But what you do see now is the gas and dust that the starlight that you see here is interacting with, and new stars are forming in all these little fingers of gas and dust that you see around here. And interestingly enough, the most robust star formation ongoing in this picture is not where you think it is. It's up here in this area where you don't even see anything in the Hubble image. And what you see up here is this red is molecular hydrogen gas that you're seeing dominate the nebulosity up here that you don't even see hardly on the Hubble wavelengths. And this is where the most active star formation is going on right now. These stars have already formed and are starting to blow this material away from themselves, where up here we actually have ongoing star formation going on. So again, different things are seen in the infrared light. Here's just a few other pictures. Again, it's just such tremendous interesting stuff in these images. This is a new star in our galaxy that's forming. It's down here hidden in the center of this cone, this bifurcated cone. There's a little dust shell right around the star that's blocking out the star, and the material that's trying to blow away from the star goes out in two cones in opposite directions from the star. Again, we're seeing structures in here that you just can't see at optical and ultraviolet wavelengths. Here's a couple of other regions of star formation in our galaxy where you're starting to see into where the stars are forming in the densest parts of the tip of that dust pillar there. And here's the famous pillars of creation over here, seen in the infrared now. There's a Hubble picture that shows these same pillars, but they look totally different in the infrared. Here's another example of a couple of merging galaxies where the optical ground-based, I'm sorry, there's a Hubble picture shows these two galaxies merging with a lot of dust and gas in the way. And again, you're seeing that there's actually an active galaxy nucleus in the center, forming from these merging galaxies that you see the merging galaxies in a whole different light. Here, there's about 270 million light years away. Incredible. And then this is an actual picture down here in the lower right. These dust shells around a Wolf-Rayet star. A Wolf-Rayet star is a very massive, very hot star, and they evolved pretty quickly by stellar standards over a period of a few million years instead of billions of years. And this particular one might be in a binary with another star that we don't see. And as that binary interaction happens periodically, it throws off another shell of dust and gas around it. And we're seeing these multiple shells that have been lost in the past. And you see very regular thing happening there. And those are literally shells of gas that are slowly moving out from that star that are thrown off periodically as its binary companion comes in close and causes it to lose more material around the outside edge. Pretty incredible. So I don't know if you've seen it or not, but back in September, the United States Post Office actually issued a Webb stamp. If you haven't seen those, you should go to your local post office, see if they have any of those left, and get yourself a sheet of Webb postage stamps for your collection. And with all those things that I've showed you, I think one of the things that's really interesting is to think about the unexpected, things that we'll see that we didn't even anticipate. And I love this little painting of somebody pulling back the curtain and looking out at the universe the way Webb sees it now. And we're really already starting to see things that were unexpected. When Hubble launched, we knew of no exoplanets, zero. Now we know of 5,000, since it's been up there. So new things will be discovered, and Webb will get used to look at things that we have no idea even exist at this point. And so it's going to be very exciting for a long period of time. So, and with that, I'll thank you for listening. And if you have some questions, we'll be glad to try to answer them for you. Thanks for listening.
I actually have a quick question. So first of all, I'd like to say that all the information you put was really fascinating because as an organization, we actually use this website to take photos of objects ourselves. So to see the comparison from the James Webb Telescope to our pictures was really like mind-boggling because yours was really had a lot better quality.
Yeah.
So my question is that you said the Hubble was after 30 years, it's still it's still working. So I was wondering how much longer do you think the James Webb Telescope would be able to function?
Yeah, good question. Yeah. We're hoping to get at least another 5 years out of it. The overlap with Webb is really valuable to be able to look at things, especially if there's a time variable phenomena, to look at them with both telescopes and get the ultraviolet, optical, and infrared data on the same object with the same kind of quality data and whatnot. Is very, very, very useful for a lot of different science things. So the reason Webb is still operating is the fact that it was visited a number of times since launch, where things were repaired, the instruments were repaired, new gyros were put on for the pointing, new solar panels, all that stuff. But literally the last time it was visited now was in May of 2009, and we're just extremely lucky that it's still working so well without any further visits to it to repair anything. They did a really good job in 2009 when they went up there. Everything was working perfectly. They had new gyros on board, new everything. And so it has been working very well. It's showing some signs of age, in particular for its ultraviolet sensitivity. The instruments that look at the ultraviolet light age with time, just from the pounding of the ultraviolet light onto the detectors. They lose some of their sensitivity, and they have to play a lot of games to try to find a new piece of the detector that hasn't been damaged by the ultraviolet light and that kind of stuff. So it's slowly losing some capability. That's not to say that it couldn't have a serious problem tomorrow and be done. I mean, the space is a nasty place, and we don't know when it's going to have a major problem. It's had a few minor glitches where it's taken offline for a couple of days while they check it out and understand that it was maybe just a high energy particle hit one of the electronics or something like that. And they reboot things and get it going again or whatever. But it literally something major could happen tomorrow. I mean, it's at that point that it's feasible, but they expect it to operate at least another 5 years. They're hoping for that. And again, the overlap with Webb is very valuable. So.
Thank you.
Yep. Are people doing things in the chat, or are they going to come on and talk?
Well, there's one question in the chat currently.
For the sun shield component of the telescope, is there any technology that attempts to possibly absorb the energy, such as a solar panel, possibly for use on the telescope? Well, they have solar panels dedicated to providing the electricity for the observatory, and those are much smaller than the sun shield. We get plenty of solar energy. 200,000 watts is way more than is needed to run the observatory. I wish I had the number. I don't. I think it takes less than about 2 kilowatts to run everything on the observatory. So 200,000 watts is more than enough solar energy. And they just have a couple of regular solar panels on the sun side that accommodate the electric needs of the telescope. So I could tell you a little story about, I told you about the mirrors that are made out of beryllium. And so each of those segments, those hexagon segments of the mirror are a different part of a curved surface. So no two are exactly alike. And they have to be ground to be the right part of the curve so that they all work together as one surface when it's all put together. And like I said, they have to manufacture and grind these things at room temperature. And I said that beryllium has a low coefficient of expansion, but it doesn't have a zero coefficient of expansion. And so it does change shape somewhat as you cool it down to 40 degrees above absolute zero. And so for each of those segments, what they had to do is grind the right shape onto the thing at room temperature, measure it very carefully, cool it down to 40 degrees above absolute zero, measure it again, see how it distorted slightly, warm it back up, grind the wrong shape into it at room temperature, and then cool it down again and see if you got the right shape when it works at 40 degrees above absolute zero. And they had to do that for each of the 18 segments of that mirror to make this perfect, absolutely perfect mirror. It's just incredible how well, when they got it all lined up and everything. A lot of the first month of science operations or of commissioning operations for the telescope was getting those 18 segments of the mirror all lined up perfectly so that they were focusing the light from the same star in the same spot perfectly and producing those beautiful point-like images of stars that you see there. So it took a lot of back and forth with the telescope to get all those mirrors lined up and working together as one. And then they still monitor it over time. Every once in a while, something will come along and, since it's just exposed out to space, anything that's flying around out there can just come in and hit the mirror. We've already had a few things come in and hit the mirror, and they can tell when that happens because it knocks one of the mirrors a little bit out of alignment, and they can actually sense that and line it back up again with sensing equipment that they have on board. So it's monitored constantly, and it's constantly being realigned if things get knocked a little bit out of alignment. So that's part of the operations. How do you think the Webb telescope could lead to further innovation? Well, I think that a lot of the innovation that's going to come out of Webb has happened or is happening based on what they had to do to make this telescope. Basically, there was a lot of technology development before they ever started putting the telescope itself together. And that includes the detectors, it actually includes the software that they use to process these images. Image processing is a very specialized thing, and infrared light image processing they've taken some of the things they've learned for web applications, and they've used it in medical imaging now. So there's a lot of different spin-offs, not just the hardware technology, but even in the software and whatnot that are being used in other areas. But since most of that is in place now for web, I'm not sure that ongoing there's going to be a lot of spin-offs from that. But the technology development from the construction phase was very significant. So I can tell you that the part of the project that I oversaw is not the hardware development and the testing, but the software systems that allow astronomers around the world to propose to NASA to use the telescope. There's a whole set of simulators for the instruments, so people can estimate how much time they need to ask for on the telescope with the different instrumentation setups and whatnot. And then to handle the proposals that come in, NASA runs a peer review. I'll just tell you that the second cycle of proposal requests just came in a couple of weeks ago. While the most proposals that they ever got for Hubble in one cycle was about 1,200, and that's about how many proposals they got for the first cycle of Webb. They got 1,600 proposals from people all around the world to use the telescope over the coming year. And NASA now has to assemble panels of scientists, peer review, to look at those 1,600 proposals and pick the subset, and it'll probably be about it's probably 6 or 7 times oversubscribed at that level. So many of the proposals are really good science proposals, but they just won't get done this cycle because there's just not enough time. People are asking for way more telescope time than we can provide in a given year. And so some of those proposals may come in again next year if they don't get through this time. But there's a big peer review process that's in process right now for the second round of proposals that have just come in for the Webb telescope. Well, what system handles all those proposals? Well, it's the system part that I was partly responsible for, along with the documentation and stuff that people use to write those proposals. And that's that maybe it doesn't sound too glamorous, but that's the part of the project that I've worked on, that enables people to write these proposals and get their data from the telescope. So every time I see one of these results come out, I say there's a little piece of me in those results, even though it wasn't my science project. It's still they had to use my system to get their time on the telescope. So.
If anyone doesn't have any other questions, I'd like to ask, what kind of advice would you have for people who are trying to get into astrophotography and trying to get into the creation of a telescope and whatnot?
So one of the great things about astronomy, I think, is that you can enjoy it at so many different levels. And so, taking pictures, astrophotography and whatnot is a great hobby. It's a great thing to do. It could even be, you could even do some science with some of the amateur setups that people have now, because the equipment that is available even for amateur astronomers has gotten so much better over the last, 10, 15 years. The CCD cameras that are available, the image processing that is available on your home computers and whatnot. I wished I'd had that when I was getting my PhD back in the 1980s, because I see stuff now posted on Facebook that blow away anything I did for my PhD thesis in terms of imaging quality and whatnot. And they're being done with a lot smaller telescopes than what I had available back in those days. So you can do a lot of stuff, and there's just so many resources out there now to help you learn how to do the image processing or the equipment, what's the best equipment to do for the different kinds of photography. Now, if you want to do long, wide field photography as opposed to telescopic, zoomed in on individual objects, there's a lot of parameter space out there you can explore to do things. I mean, this picture that's on the screen right now is obviously just a wide field picture that somebody put their camera on a tripod, but even so, you don't just click the button and have a picture like that come out. That took a lot of image processing to make that happen too. And people get very creative and have done some wonderful things with amateur stuff. Now, if you want to get into it more at the professional level, obviously getting a strong physics and math background is crucial. In the early stages, people tend to want to get right into the astronomy stuff, which is great, but you can't do professional astronomy without doing the physics and math in the background. And sometimes it's by math, I sometimes mean, trigonometry and geometry and all that stuff, but also, computer programming and all that kind of stuff. There's many opportunities besides doing the science in supporting science. There's 700 people that work at the Space Telescope Science Institute to run the Hubble telescope and to run the Webb telescope. And I want to tell you, they're not all PhD scientists. A lot of them are very good technical people that have, BS in computer programming or whatever, some technical field, that are applying it then in support of astronomy and astrophysics missions with NASA. And so there's lots of different career paths you can think about in getting involved in professional astronomy, as well as obviously doing university teaching and research type stuff like I do. So
I would like to ask if, since we don't have everyone here today, is it okay if people who watch the recording have any questions if they could contact you and where they could?
Sure. You can email my Hopkins email address, and it's my first letter of my name, W. Blair, BLAIR, at JHU, that's Johns Hopkins University, jhu.edu. W. Blair at jhu.edu.
All right, thank you.
All right.
Okay, I think that's all the questions for now. So I'd like to wrap it up, and I'd like to say thank you for coming, and thank you everyone else for coming as well.
All right. Thank you.
Thank you.
Take care.
Me too.